Hello! Today we're diving into a fundamental concept in precalculus: transformations of functions. By the end of this video, you will be able to construct a function that is a transformation of another function. The learning objective is to construct a function that is an additive or multiplicative transformation of another function. We'll be taking a parent function, like a parabola or a line, and changing its position, size, and direction to create a brand new function. Think of a parent function as the original clay you're working with. A transformation is how you mold that clay into a new shape. Let's get started with the basics. Vertical translations. Our first type of transformation is a vertical translation, which shifts a graph up or down. The rule for a vertical translation is g of x equals f of x plus k. Here, f of x is our parent function, and k is the constant we're adding to the entire function. Since we're adding k to the output, or the y value, the graph moves vertically. If k is positive, the graph shifts up. If k is negative, the graph shifts down. In other words, we're simply adding or subtracting a value from each point's y-coordinate. Let's see an example. We'll use the absolute value function as our parent function. Our parent function, f of x, is the absolute value of x. Now, let's create a new function, g of x, by adding 3 to f of x. So, g of x equals the absolute value of x plus 3. Since we added a positive 3 to the outside of the function, the graph of g of x will be the graph of f of x shifted up by 3 units. Every point on the graph of f of x moves up 3 units. For example, the vertex moves from 0, 0 to 0, 3. Notice how the entire shape of the graph remains the same, only its position has changed. What if we subtracted a value? Let h of x equal f of x minus 4. Which is the absolute value of x minus 4. Subtracting 4 shifts the graph down by 4 units. The vertex is now at 0, minus 4. This confirms that adding a constant outside a function results in a vertical shift. Next, let's explore horizontal translations, which move a graph left or right. The rule for a horizontal translation is g of x equals f of x plus h. This one is a little trickier because it feels backward. We are adding a constant inside the function to the input x, not the output. This affects the x-coordinate, causing a horizontal shift. Here's the key. A plus sign inside the parentheses shifts the graph to the left, which is in the negative direction. A minus sign inside the parentheses shifts the graph to the right, in the positive direction. Let's use our absolute value parent function again. Remember, our parent function is f of x equals the absolute value of x centered at the origin. Consider the function g of x equals the absolute value of x minus 2. Since we see minus 2 inside the absolute value bars, this will cause the graph to shift 2 units to the right. The entire graph of the absolute value function moves 2 units right. The vertex, which was at 0, 0, is now at 2, 0. Again, the shape doesn't change, only the horizontal position. Now, let's look at h of x equals the absolute value of x plus 3. The plus 3 inside the function means the graph shifts 3 units to the left. The vertex moves from 0, 0 to minus 3, 0. This backward behavior is something you just have to remember for horizontal transformations. If the change is inside the function, it affects x, and it does the opposite of what you might expect. Next, let's explore vertical dilation and reflection. These transformations change the size or direction of the graph. The rule for vertical dilation and reflection is g of x equals a times f of x, where a is a non-zero constant. Because the constant a is multiplying the entire function f of x, it affects the output, or the y values. This means it stretches or compresses the graph vertically. Here's how a behaves. If the absolute value of a is greater than 1, the graph is stretched vertically. If it's between 0 and 1, the graph is compressed vertically. And if a is negative, the graph is reflected across the x-axis, flipping it upside down. Let's use the parent function f of x equals x squared, the simple parabola. We'll start with our basic parabola, f of x equals x squared. First, let's examine g of x equals 2 times f of x, which is 2x squared. Since a equals 2, which is greater than 1, the graph will be stretched vertically, making it look thinner. Notice how the y values are now twice as large for any given x, causing the parabola to rise more sharply. It's like pulling the graph upward from the top. Now let's look at h of x equals 1/2 f of x, or 1/2 x squared. Here, a equals 1/2, which is between 0 and 1. This will compress the graph vertically, making it look wider. The y values are now half as large, so the parabola opens up more gradually. It's like pressing down on the top of the graph. Finally, let's consider a reflection. Let j of x equal negative f of x, which is negative x squared. The negative sign flips the graph over the x-axis. A standard parabola opens upward, but negative x squared opens downward. This is a reflection. Just like we had vertical stretching, we also have horizontal dilation and reflection. And as with horizontal translations, these will affect the x-coordinates in a seemingly backward way. The rule is g of x equals f of b times x, where b is a non-zero constant that is inside the function with x. Because b is multiplying the input x, it affects the horizontal dimension of the graph. The factor for horizontal stretching or compressing is 1 over the absolute value of b. If the absolute value of b is between 0 and 1, the graph stretches horizontally. If it's greater than 1, it compresses horizontally. A negative b causes a reflection over the y-axis, flipping the graph from left to right. Let's use the parent function, f of x equals the square root of x. Here is the graph of the square root function. Consider g of x equals the square root of 2x. Here, b equals 2. Since 2 is greater than 1, we might expect a stretch. But because it's a horizontal change, it does the opposite. The graph will be compressed horizontally by a factor of 1/2. This means every x-coordinate is divided by 2. The graph is squished inwards toward the y-axis. It compresses horizontally. Now let's look at h of x equals the square root of 1/2 x. Here, b equals 1/2. Since 1/2 is between 0 and 1, the graph will be stretched horizontally by a factor of 2. This time, every x-coordinate is multiplied by 2, causing the graph to expand away from the y-axis. It stretches horizontally. And finally, let's see a reflection. Let j of x equal the square root of negative x. The negative sign inside reflects the graph over the y-axis. The original graph only existed for positive x values. The transformed graph now only exists for negative x values, having been flipped from right to left. Now that we know the basic transformations, we can combine them. When you have multiple transformations applied to a single function, the order in which you apply them matters. The recommended order is to follow the order of operations, or PEMDAS. First, do reflections and dilations, which are multiplication. Second, do translations, which are addition. This means you should first handle the multiplicative changes, the a and b values for stretching, compressing, and reflecting, before you tackle the additive changes, the h and k for shifting. Let's work through an example using the quadratic parent function, f of x equals x squared. We want to graph g of x equals negative 2 times the quantity x plus 1 squared, plus 3. That's a lot of things happening at once. Let's break it down step by step using our order of operations. First, we identify the multiplicative changes. The negative sign out front means a reflection over the x-axis. The 2 out front means a vertical stretch by a factor of 2. Second, we identify the additive changes. The plus 1 inside the parentheses means a horizontal shift to the left by 1 unit. The plus 3 at the end means a vertical shift up by 3 units. So, we start with the vertex at the origin. We don't move it yet. We apply the multiplication, we reflect it to open down and stretch it to be thinner. Now we apply the addition. We move it left 1 unit and up 3 units. The new vertex is at minus 1, and our final graph, g of x, is a thinner upside-down parabola with its vertex at minus 1, 3. Our final topic is how these transformations can affect the domain and range of a function. The domain is the set of all possible x values, and the range is the set of all possible y values. Most additive transformations, vertical and horizontal translations, do not change the domain or range of the parent function. For instance, shifting a parabola does not change the fact that its domain is all real numbers. However, multiplicative transformations can definitely change the domain and range. Vertical stretches and compressions affect the range. Horizontal stretches, compressions, and reflections can affect the domain. Let's look at a square root function again, as it's a great example. Our parent function is f of x equals the square root of x. Since we can't take the square root of a negative number, the domain is x greater than or equal to 0. Since the square root of a positive number is always positive, The range is y greater than or equal to 0. Now let's transform it to g of x equals negative 2 times the square root of x minus 3. First, let's find the new domain. Inside the square root, we have x minus 3. So, we must have x minus 3 greater than or equal to 0. Solving for x, we get x is greater than or equal to 3. This horizontal shift changed the domain. The new domain is x greater than or equal to 3. The graph starts at x equals 3. Now for the range. The base square root function gives values from 0 to infinity, but we're multiplying it by negative 2 and then adding nothing. Multiplying by negative 2 makes all the positive outputs become negative, so the new range will be y less than or equal to 0. The vertical stretch and the reflection over the x-axis changed the range to y less than or equal to 0, so our final graph starts at 3, 0, and goes down and to the right. Let's quickly recap our essential teaching notes to solidify what we've learned. First, always identify the parent function. This is your starting point. Second, remember the difference between inside and outside changes. Inside changes affect the x-axis and are often counterintuitive. Outside changes affect the y-axis and behave as you would expect. Third, the order of transformations matters. Apply multiplication, stretches, reflections, before you apply addition, shifts. We have now learned how to construct transformed functions using vertical and horizontal translations, as well as vertical and horizontal dilations and reflections. We've also touched on how these transformations can affect a function's domain and range. By understanding these core concepts, you've gained a powerful tool for analyzing and sketching the graphs of a wide variety of functions. Keep practicing, and you'll master this in no time. Thanks for watching.